How far will sound carry in the ocean? From what distance can I detect a signal of interest, such as the vocalization or echolocation click of a whale or dolphin, or maybe the sound signature of a boat at the surface? This is a very common question that we get from SonarPoint users, but the answer is somewhat complex. In this tutorial, we'll aim to give you a basic understanding of sound propagation in the sea, and we are dividing this tutorial into 3 parts. In the first part, we'll look how sound really propagates in the sea, what the factors are that affect detection range. In the second part, we'll actually listen to a number of sound recordings with various background noise to give you a better understanding how this really works. And then in the third and final part, we will use an Excel spreadsheet as a calculator to obtain some estimates for some sounds. All right, let's start here with part 1, sound propagation in the sea. This is a graph that we generated some 20 years ago for our underwater acoustic positioning systems, but the same theory applies to just listening for underwater sounds, so for passive acoustic monitoring. Sound starts out, here we have a sort of a communication between a submerged vehicle and a boat on the surface, and so sound starts out with a certain strength. The source power level measured at a reference distance of 1 meter and expressed in decibels respective a sound intensity of 1 micropascal. And then as the sound propagates further away from the boat, it will naturally get weaker and weaker due to spreading losses. Spherical spreading loss or cylindrical spreading loss simply means that the wavefront gets larger and larger as it propagates further and further away from the source, and therefore the signal by necessity must get weaker and weaker, just like a tone on land will of course be more faint, perceived more faint if you're at a greater distance away from it. Fairly straightforward so far. Second thing though is that sound doesn't necessarily always propagate in a straight line, but it can get refracted by thermoclines or thermal gradients in the water, and it may also bounce off a thermocline, creating a shadow zone. So no matter what, if the water profile, the CTT profile, so conductivity, which is salinity, temperature, and depth, which is pressure, create shadow zones, then if you're inside a shadow zone, you will not get a signal, even if otherwise there would have been plenty of signal strength to reach that distance from the source. Third, sound also gets absorbed by the seawater, and that is a frequency-specific effect. The higher the frequency, the greater the rate of sound absorption, and it's expressed as decibels per kilometer, like 8 dB per kilometer or whatever the case might be. And this is on top of the propagation losses. So you also have the absorption losses. Then if you have blockages in the way, here we show some kelp, that affects the distance that you can reach, of course. And then finally, there will be various ambient noise, like this little snapping shrimp indicated here, making biological noise, and that can obscure the sound of interest, your target signal, and thus your detection range would be reduced as well. Let's take a little bit closer look at the refraction issue. And what you see here is on the left side the sound speed, and you can see that the sound speed here gets lower due to a lower temperature, and then eventually rising pressure raises the sound speed again. So sound is always refracted towards the area of lower speed of sound, and lower speed of sound will be experienced at lower temperatures, thus this downward shift as you're going into cooler water. And as pressure rises, higher pressure relates to a higher speed of sound, and so the wave gets refracted up again, like this. Now, these distances here where pressure comes into play, we're talking hundreds and thousands of meters of depth. A lot of the work that you're doing with passive acoustic monitoring will just be in the very first portion here, because your water will be quite shallow. Say the sea floor is here, and then if you were to position a SonarPoint recorder here while your sound source is here at the surface, you would not get a signal. So refraction imposes some limit on how far your signal can reach. Let's look next at spreading losses that occur, and they can be either spherical or cylindrical. And so spherical spreading loss is simply indicated here. We have a sound source in the center, and as the sound wave propagates out in all directions throughout the water, like a balloon that you're filling up with air, for each doubling of the radius, doubling of the distance, you will have 4 times the surface area occupied by this wavefront, and therefore 1/4 of the power per unit area on this surface. And that gives us the spherical spreading loss, which mathematically is 20 times the log base 10 of the distance that you are at, with a reference distance being 1 meter. Then once you reach the sea surface and the sea floor, the sound cannot go in those directions any further. And sometimes folks assume you're now moving to spherical spreading loss, where the loss is for every doubling of the distance, you will get 1/2 the power. 10 times the log of the distance then applies. So 20 times the log here, and then 10 times log. In reality, though, sound can also get lost as it's getting reflected at the surface, or as it seeps into the seafloor. And so I like to assume spherical spreading loss throughout, which will give you a conservative result. Next, we're going to look at the noise levels, and the higher the noise level, the more it will obscure your signal of interest, the less the range. Back in 1962, Wentz came up with this chart. It's still very popular, the Wentz chart. And here on the y-axis, you see the signal strength, decibels respective 1 micropascal. It should really say 1 micropascal square per hertz, or that's the best expression actually. So the micropascals are actually a square of power, so therefore 1 micropascal square per hertz, or also written 1 micropascal per square root of hertz, which works out to the same thing. And as you can see, at lower frequencies, you tend to have higher sound intensity, and then at higher frequencies, less and less. It relates to sea state, for example. You know, here we are at 40 decibels in pretty quiet seas, between 1 kilohertz and 10 kilohertz, let's say here. And then if you have a higher sea state, you're up here. Here's usual traffic noise and some other conditions. Here on the right, we see an updated version of the Wentz chart, this time with certain observations. Actual acoustic observations are indicated here. For example, this yellow line with the greenish marker in the Korean Strait off Busan. There's a reference exactly what this is about. You can see a number of observations, but you see the general trend that at lower frequencies there will be a greater sound intensity observed, and at higher frequencies a lower sound intensity. The solid gray line is meant to indicate what sort of the typical maximum noise level is that's observed at a certain frequency, even though you can see there's certainly outliers here in Harbor of Long Beach, and this dashed line, the normal observed minimum. If we go, for example, to 10 kilohertz here, the minimum might be around 30 decibels, and then the maximum might be around, just under 60 decibels or so. If you go to 100 kilohertz, even the maximum is down to 35 dB or so. Now, here are actual spectra of sound observations that we did with the SonarPoint recorder, and in some cases with the predecessor of it, the Micromars recorder. And let's take a look what we learned here. First of all, I want to point out the hydrophone self-noise of the SH33-2 configuration. And here I recommend that you take a look at the hydrophone selection tutorial. You can see that this particular hydrophone, actually its response curve or its self-noise flattens out once you reach 2-3 kilohertz here, 3000 hertz. And then as we see some of our observations here, like the gray line, which is in Monterey Bay, reached a similar level, somewhere above 10 kilohertz. And so the noise there's still going to be noise in Monterey Bay, but we can't quite pick it up anymore because our noise flow of the hydrophone is too high. Now again, if you go back to the hydrophone selection tutorial, you might want to reprogram your hydrophone to the -S2 configuration, which will allow your self-noise to keep going down, 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 down with higher frequency. And now you might pick up some very faint signals here, right? Beyond this, let's take a look at a very noisy signal. Here's a signal of a ferry that was passing within 400 meters of a Micromars recorder in Friday Harbor, at the Friday Harbor terminal. This ferry had a very distinct continuous tone at 400 hertz. I'm not quite sure what that is. And then broadband noise that was very high, pretty much the highest observed among the various examples here, and very broadband, but following the general trend of declining with higher frequency. Here, snapping shrimp in Monterey, and you will hear them later, also produce a very broad and strong peak here, and that can really limit your detection range quite a bit. So you want to be aware of where snapping shrimps occur, and they are widespread. You can get them in sandy conditions, sandy bottom or on reefs, so be aware of that. Here, the Catalina Deep Channel is near Catalina Island in Southern California, actually rather quiet, Here you see this is at a depth, by the way, of 100 meters. We lowered Micromars recorder 100 meters down, and we detected a rather, still faint, but very noticeable sonar signal around 3 kilohertz. This may be an anti-submarine sonar. It's a dual tone sonar around 3.3 kilohertz here. You can see how that really sticks out of the background noise. But now imagine if your background noise was really what you have here in Monterey Bay, then it wouldn't really be any stronger than the background noise, and you would start having some detection problems, and we'll look at that later. And then other conditions are somewhere in between. This one here is near the 1 mile buoy offshore from Moss Landing in Monterey Bay. It's certainly more quiet as far as the snapping shrimp here is concerned. In Monterey itself, this one is at Del Monte Beach in 20 meters of water, and here again, Moss Landing at the 1 mile buoy, maybe 100 meters of water or so. Quite a bit more quiet, not as quiet as deep 100 meter down in the Catalina Channel, where you're away from some of the surface noise. And then this green line here is at a dock in the Baltic, see at a very quiet night, what you see, these spikes here are actually, again, the older micromars that had some self noise. You see that here. So it was a very quiet night, and that was the sort of the quietest recording that we have seen so far. Here's a summary of what we have learned so far. As far as detection range, the first factor is source power level. The stronger signal will travel the furthest. Each additional 6 dB of SPL translates to a doubling of detection distance if you're assuming spherical spreading loss, and that's for short distances. Then at long distances, these additional 6 dB will make less of a difference because now you are limited by absorption losses. Refraction. Sound will always refract towards an area of lower speed of sound, which is associated with lower temperature, so refraction towards deeper water at the surface. Lower pressure, which is refraction towards the surface at great depth, but a much less pronounced effect, and lower salinity. And this can create shadow zones, and if you happen to be in a shadow zone, then you can no longer detect the sound. We have certain experience values for shallow water operation with a recorder located near the seafloor. You might get reliable detection is our experience value up to 25 times the water depth. You can assume a usual detection range of about 50 times water depth. And if you get lucky, you might get 100 times water depth. So this will be a limiting factor independent of everything else. Spreading losses, those losses may be spherical, which means you have a 6 dB loss for every doubling of the distances. So it's more pronounced at short distances. Or cylindrical loss, you can assume minus 3 dB for every doubling of distance. I like to assume always 6 dB, be on the conservative side. And again, most pronounced losses, the steepest gradient for spreading losses are at the shorter distance, where the doubling distance is the least. Absorption losses are expressed in decibels per kilometer, therefore they become dominant at longer distances. These are frequency-specific losses, and higher frequencies absorb at much greater rate. As a rule of thumb, if you have a signal of around 30 kilohertz, you might get a detection distance limited by absorption losses of a few kilometers. If you are operating above 100 kilohertz, then your detection distance might be a few hundred meters. So that would be, say, for harbor purposes, vocalizing in the range between 100 and 150 kilohertz. And finally, ambient noise will always obscure or compete with your signal of interest and therefore limit the detection range. All right, let's look at some actual sound recording examples. And the first one is a sonar that we detected in the Catalina Basin, as well as possibly some geological noise. I'm not really quite sure what it was. Let's go to Google Earth here for a moment. We were located out here, and we lowered it was the micromars recorder to a depth of about 100 meters, and we were out in the Catalina Basin. If you look here in the lower right corner of the screen, you can see that it's about 4,000 meters deep, so sound can certainly travel a significant distance, and we can get into the deep sound channel where it can travel a very long distance, as you have seen in our refraction chart earlier on in this tutorial. So let's go back to the signal itself. Here in the time domain, it doesn't look like much. And then what I'm doing in both examples, this is the first of two examples, I'll overlay it with certain noises. This is noise from snapping shrimp, primarily observed with a SonarPoint recorder at Del Monte Beach offshore the Naval Postgraduate School in Monterey at a water depth of about 20 meters. And this overlay, the second one, is both the snapping shrimp noise and noise of a ferry near the closest point of approach, about 400 meters from the recorder, 400 or 500, not quite sure, from the recorder location at Friday Harbor in the San Juan Islands, that is in Washington State, in the United States. So let's listen to the first one. And what I'm going to do is, rather than viewing the time domain waveform, I'm going to go to a spectrogram waveform here, and let's listen to it. Here you hear the sonar, and it fades away. There was again a weaker sonar instance, and this type noise may be geological. Now the same thing with snapping shrimp. You may have heard the sonar a little bit, and then we're coming up on the presumed geological noise here. And now also with ferry noise added. And you can see that it's very hard to discern the sonar noise or the presumed geological noise here. What I'm going to do now is see how it stands out when I plot a spectral, just a frequency analysis, I should say. Plot spectrum. Okay. And here we can see very clear now the sonar at 3 kilohertz. Now I don't have quite enough frequency bins to resolve it into individual bins. Let me see if I can do that. Here we're starting to resolve it. See that? Okay, it's really two distinct peaks at, what do I have here? 3.2 kilohertz, and the other one is at 3.4 kilohertz. Now, if I look at the same area but overlaid with the snapping shrimp noise, so here we can certainly quite clearly see it here. Visually, I can still see it a little bit here, the sonar, and I'm going to do my analysis here. Plot spectrum, and yeah, there's something here, but you know, all the snapping shrimp background noise makes it quite uncertain. So for an automated detector, we might have some problems here. This is 4096 bins, and I still can just so see the sonar signal sticking out of the noise. If I go back to 512, let me see what I get. Yeah, there's something there, but you know, you might well mistake that for more snapping shrimp noise. So you can already see the background noise obscuring your signal of interest here. And as I'm getting to adding the ferry noise, a ferry at 400 or 500 meters, yeah, it gets very difficult, and we may not be able to discern this sonar, which probably was many tens of kilometers away, and we would not be able to discern that in the context of a passing ferry. I'm gonna just go over here roughly the same area, see if I get anything. Plot spectrum. Yeah, not really. Let me go to, again, a higher resolution. There's something here, but that's actually the ferry itself at 400 hertz. Here in the 3 kilohertz range, it's pretty much lost. So you see the impact that the snapping shrimp and then the ferry noise, two types of ambient noise, can have on your detection range, and it can be quite pronounced. This is our second sound example. This time we have echolocation clicks of a killer whale and then a whistle of a killer whale, probably quite close by. And here again overlaid with the snapping shrimp noise and then the ferry as well. Looking at just the time domain waveform, the clicks, the echolocation clicks, do stand out, so you could detect them certainly by looking at them or by just thresholding in the time domain, and even the whistle of the killer whale is a dominant noise without any filtering, and so some time domain analysis here would work in the context of the relatively low ambient noise observed at the site. Again, this is at San Juan Island, on the western shore of San Juan Island. Then as we overlay it with snapping shrimp noise, then detecting the echolocation clicks is not really possible anymore in the time domain waveform. Similar thing with the whistle of the orca, and then of course it looks quite hopeless here if we have the ferry noise as well. But there's other analysis techniques, and so again we're going to go to a frequency analysis here. And before I play it, I'm just going to zoom in a little bit on the time axis here. This should be fairly good. And let's just listen to it now. You can already see here, these will be your echolocation clicks. Sounds like hammering, right? And here we're coming up on a whistle, and you can see it quite nicely here. And now see if you can see the same patterns as we are overlaying it with snapping shrimp noise. Much more difficult to discern, although your ear can detect it. And the whistle, though, still stands out in this spectrogram. And now we add the ferry noise. And I think here's the whistle. And even the whistle is hard to see in the spectrogram. So once more, you can see that detection range obviously has to do with the background noise level as the signal of interest competes with the background noise, but it is dependent on your analysis method. The more sophisticated your analysis, the greater your detection range. On to the final part of this tutorial, let's do some detection range analysis. We'll start with the example of the deep sonar in the Catalina Basin that you've heard already before, and I zoomed in on a small portion of the most intense part of the signal here. This is my frequency spectrogram. You can see the signal here is at a little bit below 3.5 kilohertz, maybe 3.4, 3.3 kilohertz, like this. How strong is the signal is my first question here. Here in this frequency analysis, I see it's at about minus 44 dB. Now you have to be careful to set your bin size correctly. I set it to 1024 bins. This is a 100 kilohertz sampled recording. 100 kilohertz divided by 1,000 bins is about 100 hertz per bin. That should be about right when I look at my distribution here. And if I use a bin size that's too big, you will see the signal apparently gets weaker. See that here? It's not really weaker. We just have too many bins available here. So I'm staying here. Another trick is you can actually see I'm now at minus 43 about at the maximum. If I go to something lower, I'm not, it's pretty much the same. So as long as your output power, reported power stays the same, you're about right, you know, from 256 to 1000 bins. It didn't change a whole lot. Minus 43 dB. I will also look at this waveform in the time domain now. Here's our sonar signal. And what's the peak? About minus 40 or so, minus 40 dB, which translates to an RMS. You always have to subtract 3 dB for RMS, and RMS is reported in frequency analysis at minus 43 decibels. So what does that mean as to how far this sound source may have been away? For that, we will now go to the Desert Star acoustic calculator. We'll update this every once in a while. This is the versions from the 11th of June 2020. I just updated it, and in there you will find a tab called Signal Loss Calculator. And what you do is first you enter the source power level, transmit power of your source. I am guessing that this sonar may have been a Navy sonar called AN/SQS-53C, based on the frequency that it's at. It's a common sonar that the Navy uses for anti-submarine work, submarine detection. So it has an SPL of 235 dB at a reference distance of 1 meter. Now I have to select the frequency of interest. This is used to compute sound absorption. Should really be 3 kilohertz, but the lowest that I have available that I've computed our sound absorption in seawater is for 8 kilohertz. I'll briefly go to this one. It comes from this table here, and the lowest I currently have in there is 8 kilohertz. Well, I'll have to use the 8 kilohertz here. Then I'm going to define a safety margin for my detection of 12 decibels. The signal bandwidth of 12.5 hertz, that would be a very tight detection. So we'll change that here. What did we have? About 100 hertz we used. 100 hertz detection. All right. And so now what I can do is I can compare the signal strength that we observed to what it would be at a certain distance. What signal strength did we observe? It was, let me go back to this guy here, 152 dB full scale. And then we said the signal came in at minus 43 dB respective full scale, which puts us as 109 decibels. Going back to the calculator here. All right, if we were at a distance of a receiver distance of 100,000 meters, we would see a signal strength of 68 dB, but we did see 109 dB, so it must be closer than 100 kilometer. I'm going to try 50 kilometer, 50,000 meters. That gets us closer, 102 dB, 40 kilometers. 40 kilometers. So at a 40 kilometer distance for this sonar with a SPL of 235 dB, we would expect to get a signal of 109 dB. In reality, since our frequency of interest, the actual frequency of the sonar is lower, it would probably be a little bit more than 40 kilometers before we are down at 109 decibels. Let's go to Google Earth. So our location was approximately here. And where would be a 40 kilometer distance? The eastern coast of Santa Catalina Island is a possibility. Going 40 kilometers in a different direction puts us right around here. still in the middle of the ocean. San Diego is quite a ways away at 112 kilometers. Now, using signal strength to estimate distance of the sound source is a perilous thing to do. It will probably be quite uncertain. Keep in mind, we made a number of assumptions, such as that there would be a spherical spreading loss, but given the 4,000-foot depth of Catalina Basin, it could very well be that the sound traveled in the deep sound channel and the spreading loss could have been much less. So all we can really say is that locations such as San Clemente Island as a source of this sonar is a reasonable location, that it probably wasn't as close as Santa Catalina Island, but it could have really been throughout a large range here, and it would take several recorders forming an acoustic array and using time differences of arrival to locate the location. And I should add, over these larger distances, that should then also be done along with ray tracing rather than just a straight line sound propagation assumption. Let's ask a second question here. What would be the detection range for the sonar if, let's say, our noise level was the same with all the snapping shrimp as we had in at Del Monte Beach in Monterey? And there, going back to our noise observation curve, we observed a noise floor snapping shrimp dominated at the frequency of the sonar here of around 80 decibels over a 1 hertz interval. I'll go back to my calculator here. And so my detection range would be reached if the maximum noise floor that is allowed doesn't exceed 80 dB. Right now it's 89 dB for a 40-kilometer distance. I'll go a bit up. 50 kilometers, 82 dB, that's getting pretty close. 52 kilometers maybe, I'm guessing. Yep, 52 kilometers might be about the maximum distance if I allow for a 12 dB margin of safety to detect this sonar there in the Catalina Basin. Moving on to our second example now, we'll use the killer whale recording here, or let's say we are going to try to figure out how, over what distance we might detect a killer whale, an orca vocalization. And so that would be the whistles rather than the echolocation clicks. And so for my noise assumption, again, I'm going to use a Monterey Bay with the snapping shrimps there at a 20-meter depth in Monterey offshore, the Navy postgraduate school. And we had an observed noise floor of 80 decibels there. Going to my calculator, I will now plug in a reference number that I found for the SPL of a killer whale for these whistles, and it said they could be up to 193 decibels. I don't have a typical number available. It's not smart to use the maximum strength of these whistles because obviously you want to catch weaker whistles as well. But this reference also said that the frequency can be up to 36 kilohertz. And the closest I have available in my lookup table is 34 kilohertz. So I entered that here. And remember now that the noise level at the receiver location we are assuming is going to be 80 dB. Here I have 52 kilometers, I end up with minus 297 dB. That's not going to work at all. Let me experiment going down to 10 kilometers, 11 dB. Nope, that's not going to work. 5 kilometers, 52 dB. No, that's still less than 90. Let me try 1 kilometer. Now I'm at 94 dB, so that will work. Let me go to 1.5 kilometer. No, not quite. 1.25. Oh yeah, there we are. So we might be able to detect the strongest whistles of these killer whales under the noise conditions as we are experiencing there in Monterey with the snapping shrimp over a distance of 1.25 kilometer. If the whistles, however, are weaker, then our detection range would be less. So I would be skeptical of placing my hydrophones this far apart. My recorders, I would probably go for something like 500 meters. Let me see what we would get then. 500 meters. Okay. Signal strength at receiver 124 dB. So I can go down quite a bit. I could go down 34 decibels from the 193 dB and then get this signal. Although with my safety margin here, it's a little bit less. Let me try 180 decibels, 179 dB. Okay, so 179 dB whistle. I should still be able to detect with a 12 dB margin of safety at a 500 meter receiver distance. And so maybe I would go for this setting to set up my SonarPoint array. Now, one thing as a final caution here, the projection of sound from the killer whale is not likely to be omnidirectional. It will probably project most of the whistle ahead of itself. And so then, you can very well end up in the position that not all your recorders will detect the whistle if you're trying to geolocate where the whistle came from. And so then I would even be skeptical of a 500 meter distance. And what we have more typically worked with is sort of 100, 200, 300 meters for these killer whales. And that seemed to work pretty well. So this concludes our discussion of detection distance. Please do not take these numbers as being all that precise. There's a tremendous amount of fluctuation in underwater sound propagation. You always want to have rather conservative estimates, and then you would want to back it up with doing initial short deployment where you see how everything works out before you decide how to configure your array for a long-term deployment.